Okay, welcome back everyone. So today what we're going to do is, I thought I would first start off with, again, more of a general overview. I don't think I really hit on what we're actually going to be learning in the class very well. We spent a little too much time on class policies. So what I wanted to do was spend a bit of time at the start to kind of give everyone a general understanding of what the main goals are for what we're trying to accomplish in class in the long term. So for a general chemical plant, this is really the system that is going to be what we are interested in for this particular class. Now that's not to say that every person in this room, when they graduate with their degree, has to work with a traditional chemical company like Dow or DuPont, or soon they're going to be the same company, or Exxon or something like that, right? Because the same principles that are happening inside of a chemical reactor or a heat exchanger are shared within cells in the body, right? So in this class though right now, what we're doing is the general overview of what chemical engineering is from a traditional sense, right? This is the big picture perspective. In your junior year, you zoom in and you go to the micro scale, and you actually derive all of the differential equations that control mass transfer, heat transfer, chemical reactions. Right? Those are really the equations that you would be using if you were solving for, the conduction of ions through an ion channel in a cell, for example. Or, in quantum, you learn stuff about how electrons behave so you could help design a solar cell. Right? So, but in this class, though, we're really at a big picture overview. We don't care how any of these processes occur. What we are right now in this class is accountants. We are mass accountants, we are chemistry accountants, and we are energy accountants. We need to make sure that we do not violate the law of conservation of energy and the law of conservation of mass, and that we're not losing carbon atoms or hydrogen atoms. That is basically the entirety of what we are trying to accomplish in this class. Okay? But it's kind of complex. So, as I mentioned in the last lecture, what we're trying to do is trying to take a cheap material, right? And one really easy example is methanol synthesis, in which case we take water and methane. We take it through a lot of chemical processes. These could be separators, heat exchangers, reactors, furnaces, all sorts of different processes. And our goal is to produce some sort of a valuable commodity chemical. In this case here, this is a steam reforming process to make methanol. So what needs to happen though is we can say, I need to make 1 million tons a year of this. Right, and that's not an unreasonable number. Chemical plants are massive, right? Distillation columns in some of the world's largest refineries are like, they look like skyscrapers when you walk up close. They're just huge, huge structures, right? Because these all scale so that the bigger you make it, the cheaper it is to make the chemical. So if we're trying to make 1 million tons of methanol a year, how much methane do we need to purchase per hour? How much steam do we need to generate? How much of this methane do we have to purchase in addition to it going to making the methanol to boil water, right? Because you're probably going to be grabbing water from a stream or a lake. You're certainly not going to be purchasing your water from the city that's gone through the water treatment process, because you're going to be using, millions and millions of gallons of this stuff, right? So what we're trying to do in the class is basically understand everything that goes on here. Not how the reactor is designed, where the tube inlet is or where the tube outlet is. We're just looking at the big picture. What comes in and what comes out. Right, so methanol, CH3OH, we could balance this chemical reaction right now. And so we would know with stoichiometry how much methane and how much hydrogen or oxygen we need to accomplish this task. Right, but we're going to lose some of it. We're going to lose some of it to the reaction not going to completion. We're going to lose some of it to the separation not being 100%. And those are the details that we're going to be stuck in and learning about strategies and techniques to understand. In addition, it's not terribly fun if I were to just say, you're producing 1 million tons of this a year, how much methane do you have? Right? I'm sure most people could balance that reaction right now and do the unit conversions to figure out what the total amount of material is. That's not really the fun engineering part. The more fun engineering part is, we'll say, these are the physical laws and rules that methane follows. These are the physical laws and rules that steam follows. I want you to calculate what is the efficiency of the process. I want you to calculate how good the separation is. And so what we're going to have to learn is some general fundamentals of how chemical reactions occur, how separations occur, what are the thermodynamics of phase separation, because otherwise it'd be really boring. Right? I would just give you a really clear-cut question with a really clear-cut answer. But as we learn more of the real physics of how chemicals behave, then I can give you less and less and less information, and you can still solve the problem, but you have to rely more and more on thermodynamics, on chemistry, on physics. So what we're going to be spending the entire class on is this process right here. Right? But this could be a series of little processes that all connect together, and they could be intertwined with recycles and going out. So as we move on in the class, we're going to go zoom in, zoom in, zoom in, zoom in. So to start off with, we have to cover a few of these engineering basic fundamentals. Then we're going to talk about making sure we don't lose any mass. And then finally, we're going to talk about making sure we don't lose any energy. Right? So that's going to be the general flow and progression. So the 3 sections that are going to cover the first 3 midterms are going to be engineering basics, mass balances, and energy balances. Those are the 3 main topics that we're going to cover. And at the very end, we're going to do the whole thing over again, but using differential equations. Right? We're going to redo everything as a function of time. So for example, if it's a transient system, so a good example of that is draining a swimming pool or filling a swimming pool. Right? The rate that a swimming pool will drain at is proportional to how much water is in there, or draining a bathtub, for example. Right? Because you have a high pressure of the water squeezing it down the drain, but as you get closer and closer and closer to it being drained, there's less of a pressure force pushing that water out. That's an example of a transient system that we'll be talking about at the end of the semester. Okay, so hopefully that's a little bit more concrete and of an overview of what we're trying to accomplish. But for now, we're going to be starting off talking about not the process itself, but just about any particular fluid in general, how you handle it, what are the units, what do those units mean, and then we're going to go further on and get more in depth and more in depth as time goes on. So some of this material may be introductory, some of it may not be, but I like to go over it anyway, just so that everyone is on the same page. Okay. So the first thing I'd like to talk about is unit systems. So there are different types of units. The most basic type is called a base unit. This is sort of our indivisible unit type. So for example, mass, right? In SI units, that's a kilogram. That is our base indivisible unit, right? We really can't simplify the concept of a kilogram any more so. It's just mass. How do you measure mass? We've decided that we measure mass in kilograms. We have length. This could be meters. We have temperature, Kelvin, and we have other ones like time, and more complex ones that we're not necessarily as familiar with. So electrical current, the SI unit is an ampere. And we have other ones like this. But basically, is this the smallest, simplest type of unit you can? Next, we have multiple units. And this is sort of where we get into our SI nomenclature or SI prefixes. For example, giga corresponds to 10 to the 9. So a gigameter is 1 times 10 to the 9 meters. We have mega, 10 to the 6 cubes. kilo, 10 to the 3. Centi, 10 to the minus 2. Milli, 10 to the minus 3, and so on and so forth. So a kilogram is 8,000 grams. Shouldn't be news to many people. Now, the complex ones and the interesting ones are derived units. So these are derived or compound units. So we obtain the derived or compound units based on modifying our base units by multiplication or division. So we have area, which is meters squared. So it's a meter by a meter. Likewise, we have volume, which is the length dimension cubed. We can get more complex than this, and we can have units of force. And in SI, the unit of force is a Newton. In the base units, this corresponds to a kilogram per meter per second squared. So every derived unit can be simplified down to its base individual units. Now, I really stress units a lot because you can solve problems just by manipulating units, right? I don't remember every equation that I've ever learned in my life. But I know if I simplify all of my complex or derived units into their base ones, I can combine them very trivially. And so I to this day, I have a Word document that I made when I was a graduate student where I take all of these types of units, right? Units of viscosity, units of pressure, right? Even things like coulombs, right? I've taken all of those and I have broken them down into the base units. And the reason behind that is when you have a big complex equation that might have units of pressure or viscosity or some other random stuff in there, if you break it down into the base units, you can very easily verify that the units cancel out, you have dimensional homogeneity, and that you can understand the equation. So, if I'm converting from one base unit, like a kilogram, to another base unit, like a pound mass, right, as opposed to a pound force, right, that's just a simple unit conversion, right? I just look it up. More or less, someone decided how is a pound mass defined versus a kilogram defined, and then they just figured out how to multiply those two things together and convert between two units, right? So that's trivial. That's something that everyone can do just by typing it into Google, okay? However, what gets a bit more tricky is when you're converting from between different base units or between different derived units. In that sense, it's more complicated. You can't just look up necessarily a unit conversion. For some you can, for others you cannot. So for example, what if we were trying to convert from mass to volume, or vice versa? This is not strictly a unit conversion. What we need here is a physical relationship. Now, tying back this question or this problem to our overall class goal. Volume is not a conserved quantity, right? You can compress air. So if I put 1 liter of volume of a gas into a process, I could spit out a fraction of a liter, and that's totally fine. Mass is conserved, though. You cannot create and you cannot destroy mass. So if I'm trying to build a chemical plant, I might be purchasing a gas because that's the easiest way to sell it, right? It's maybe easier to measure out the volume of a gas, but I need to know what the mass of that is, and I need to know how many moles of that is in order for me to actually do all of my math. So to make the class more interesting and to make problems more realistic, we have to be able to convert between different properties of different fluids. What is the physical relationship that everyone here knows about that converts between mass and volume? Density. So So in this case, we need density. But density is not just a single number that you can look up or that Google can do a translate for you and do a unit conversion. Right? It is a real fluid property, so we need to understand the fluid properties. In the case of density, it is defined as the mass over the volume. Alternatively, most people have not heard of this other unit, the specific volume is exactly the density, but just the reciprocal. This is the volume per unit mass. Right, so these are the physical relationships that we need to translate one type of variable into another that allows us to set up our equations. Now, later on in the class, we'll be talking about equations of state. Has anyone heard of an equation of state? Yes?
There's enthalpy. Is this state function?
So those are state functions.
Okay, so not the same.
But equations of state, well, so equations of state are actually more useful in thermodynamics. So you can actually use equations of state to calculate state functions. And that's really what they're useful for. We're going to use equations of state in their most basic of levels. I 100% guarantee everyone knows of an equation of state. Yes?
Are you talking about the Gibbs phase rule?
Not quite.
Gibbs free energy?
No, so nothing to do with enthalpy, Gibbs, or something like that.
Ideal gas law?
Ideal gas law. That is an equation of state. Okay, so the ideal gas law relates between three properties of a fluid: the temperature, the pressure, and the specific volume or the density, right? V hat. So if we write out the ideal gas law, PV equals nRT. This is the form that most everyone is likely familiar with. This is not the form that I generally like to think in. I like to think in PV equals RT, where V is the specific molar volume, meters cubed per mole, right? That's essentially the density of the fluid, right? It's the reciprocal of the density. But what we're looking at here is in the equation of state, we have pressure, density, and temperature. Oftentimes you'll even see in a physical chemistry class, you might even see P is equal to rho RT. This is another really popular form of the ideal gas law that a physicist would probably prefer to use. R is a constant, right? R is related to how much energy a fluid or a gas has per unit of temperature. Right? It's a constant of the universe. The R constant is directly related to the Boltzmann constant, which basically tells us how much kinetic energy does a single gas molecule have. We can't change that. So if I change a gas temperature by 1 degree Kelvin, I give it a certain amount more energy. That is what the definition of R is. But if you look at the equation of state, you're relating between pressure, density, and temperature. So you need any two of the three to transform into the other one. Right? You can only solve for one unknown in an equation. So that's why the ideal gas law, or any equation of state, is a physical relationship between the properties of a fluid. Now, the ideal gas law is only for gases, right? It's a really bad equation of state. It's only good for low pressures and gases. The ideal gas law doesn't predict that liquids can even exist, right? So obviously we have more complex and elaborate equations of state that actually predict that liquids exist and what the liquid properties are. So in reality, in thermodynamics 2, who here's had Thermo 1? I think most everyone should have Thermo. Okay, good. In Thermo 2, you're going to be using equation of state. But this relationship here, translating between temperature, pressure, and density, that is like training wheels for equations of state, right? In reality, equations of state are used to calculate enthalpy, entropy, Gibbs free energy, and so on and so forth. If you know the relationship between temperature, pressure, and density, you can calculate enthalpy, you can calculate all these different properties. So that's the long-term outlook of what an equation of state is. For our purposes, this is it. Right? An equation of state is just a tool that's going to be used to manipulate fluid inlet and outlet streams. Okay, so a couple more definitions to go through. Specific gravity is a term that I will use a lot. So specific gravity is just so we abbreviate it SG. And the reason for this is just really convenient. It is the density of any fluid divided by the density of water at a standard temperature and pressure, STP. In this case, I believe it's not, I want to say it's 4 degrees C and 1 atmosphere. The reason for this is that's actually the densest state of water. So if you go to the bottom of the ocean floor is at 4 degrees Celsius because that's the densest state of water, because you've got all this weight of water pushing down on it. And that's what determines the temperature of water at that condition. So the reason for this is that if I tell you that the specific gravity of a fluid, Sg, is equal to 2, for example, then I know that I'm twice as dense as water. Which basically means that means I could say this is 2 grams per milliliter, or 2,000 kilograms per meter cubed, or I could do the same thing for American engineering units. So specific gravity is just a really nice, useful way to communicate the density without forcing you guys to decide which units you want to work in. Right? Some problems we'll be working on in class will be in SI, and I tend to be SI heavy. Some units that we'll be working with are in pounds and ergs and all sorts of other weird American engineering units. I tend not to prefer those just because I'd much rather focus on breadth of problem as opposed to forcing you guys to do unit conversions, because everyone nowadays can do unit conversions like that. Right? So I typically don't like to force unit conversion work. Okay. So next, we're going to talk about flow rates. So a flow rate is just a mass or volume quantity that is moving as a function of time. With flow rates, we write them as m dot. And this corresponds to a mass flowing per unit of time. And an example of this could be 1 kilogram per second. So if you're imagining sort of a pipe and there's a fluid traveling through it, you have 1 kilogram of that fluid per unit time traveling through it. Likewise, volumetric flow rates is equal to some volume over some unit time. And this could be something, let's say, like 10 meters cubed per hour. Okay. So now let's use what we've done so far and do a quick example problem. And this example is a nozzle. All right, I'm going to introduce something that we haven't talked about, but we're going to use units to solve the problem. So in a nozzle, and this could be like a hose nozzle for your outside hose, we're going to say that we have a volumetric flow rate going into the system and some face velocity, which typically we denote that as U, going into the nozzle. Coming out of the nozzle, we have a volumetric flow rate going out with some velocity going out. Now in this case here, I'm going to say that the volumetric flow rate is 1 cubic foot per second. our velocity u we're looking for is going to be in feet per second. That's the physical face velocity coming out of the fluid. Now for this problem here, I mentioned that volume is not conserved. In this case, we're going to call the fluid incompressible, meaning that its density is constant, right? So if we look at volume, right, is meters cubed times by density. Let's see, so mass is meters cubed times by the density, which is kilograms per meters cubed. So that mass is equal to volume times by density. If the density is constant, then mass and volume are essentially interchangeable, just scaled a little bit, right? But I'm not joking, guys. Like, I really don't remember this off the top of my head. I just kind of work it out based on the units I was trying to remember. Okay, so what we're going to say is that the cross-sectional area of this nozzle on the inlet is 1 foot squared. So what we're going to do is we're going to use units to answer the question, what is the inlet velocity of the fluid and what is the outlet velocity of the fluid, and did our nozzle do its job? Have we accelerated our fluid? So take a moment, right? This doesn't have to be independent. You can talk to your friend, but basically use units to solve this problem. What is the velocity in and what is the velocity out? So begin. Yeah.
When you calculate the mass there, so you said mass is equal to meters and density, right? So what is the volume and, so did you get that from like V and
Oh, okay. So that was at the end there. That's just that's mass. But you don't actually have to convert to mass because we don't know the density. So you will not. Yeah, those are just the units on the side that help you derive the equation. So just look at the units that we have. We have feet per second, and feet squared. Yeah, so if you can find a way to manipulate those variables, you should be able to convert to feet per second. And then you'll have to derive the equation.
Where are you finding again?
We are solving for the inlet velocity and the outlet velocity, but I didn't give you an equation, right? You have to derive the equation based on just manipulating the units. Yeah, question?
Do we not need the area of the outlet?
Oh, you're right, we do need it. It is 0.1 feet squared. No.
So we did this. So this is the mass. Oh, yeah. That's the same. The area.
All right, who feels comfortable with their answer? Okay, a few. Who wants to shout out? What's the inlet velocity? 1 foot per second. Outlet velocity? 10. Math was really complicated on that one. But let's go through and let's just do the same procedure that I did here, right? And then just let's rederive the equation. So we have U, which is feet per second. We have a volumetric flow rate, which is feet cubed. And we have feet squared. What we're looking for, right, is some equation that tells us the velocity, but as a function of the units that we know. So this would be, we're looking for feet per second. Okay, so let's probably not start with there. So can we manipulate these two units to give us feet per second? And certainly we can. We're going to say this is cubic feet per second divided by feet squared. And so our equation that we have just derived for velocity is the volumetric flow rate divided by the cross-sectional area. Right, but we derive the equation just by looking at the units. So our volumetric flow rate is 1, our cross-sectional area is 1 for the inlet, which means that our inlet velocity is just 1. Our volumetric flow rate is constant, right? Because we're saying that this is incompressible. So all the material that comes into the system is going to be coming out of the system. Otherwise, the nozzle would basically explode, right? It's not going to balloon out, right? That volume has to go somewhere. So in order for this nozzle not to explode, we call this steady state. The amount that comes in is the amount that comes out. So our outlet flow rate is 1. Our outlet cross-sectional area is 0.1, which gives us an outlet velocity of 10 feet per second. Right, so we can derive equations just by looking at the units. Now, in reality, this isn't the full story. Right? In fluid mechanics, you're going to talk about how the velocity is not uniform across the whole cross-sectional area, but in general, this is probably going to be a decent enough approximation for what we need to worry about. Okay, any questions? Okay, so let's move on now to some other unit types. Specifically, we'll talk about composition. So the molecular weight, right? The molecular weight is different for each material, and it converts between mass and moles. I'm sure most everyone has seen molecular weight by this point. One unit that is kind of annoying is, I don't particularly like it, but it comes up from time to time, and so it's important to have some understanding of what it is. So if we look at water, we say that this is 18 grams per mole. Now, strictly speaking, oftentimes, this is, not oftentimes, but sometimes this is referred to a gram mole. Because there's also units called pound moles. So this is 18 pounds per pound mole. I don't particularly like this nomenclature system, but sometimes it does pop up from time to time. A pound mole is bigger than a mole. So in this case, 1 gram mole is equal to 6.022 times 10 to the 23 particles. A pound mole, 1 lb mole, is equal to 424 gram moles, because there are 424 grams in a pound. I always get confused with gram moles and pound moles, so don't be ashamed if you have to Google it really quickly. But that's the whole point of this, is that you can just basically, it's kind of like specific gravity a little bit. You can choose to work in whichever units you want to, right? We don't necessarily care to solve a problem that 1 mole is 6.022 times 10 to the 23, just as long as we're keeping it consistent. right? So a pound mole physically has more particles than a gram mole does. It's not something that I think everyone should commit to memory, and go to bed studying it every night, but it's something just to be familiar with. Okay, a couple of other composition or conversions that we're talking about. Mass fraction is something we'll use extremely commonly. So mass fraction in general, we will call it x sub I. So x tells us this is the mass fraction. I tells it that it is species I. We define the mole fraction as the mass of species I divided by the total mass of the system. So how we write that generally is the summation of I equals 1 to n, the total number of components in the system of mi. So in word terms, this is mass of I divided by total mass. Similarly, we have a mole fraction. Typically, we will call this y sub I. And this we define as n of I, the number of moles of species I, divided by the summation of n of I. And in general, when I'm generalizing equations, I'm not going to put the I equals 1 to n. Right? We're typically not going to be working with any more complex of summations than that. Right? This is not going from j equals 0 to j minus 1 or something silly like that. No, we're just going to be, just add everything up. So I'll generally just write the summation here when I'm generalizing equations. This is the moles of species I divided by the total number of moles. Moles and mass fractions are things that we will use a lot. Okay. Well, let's see where should we go from here. Still is bored. Okay, just a few more units left to go. We won't be able to finish them all today, but today we'll talk about concentration. Right? All of these units have base sort of fundamental units, but they're not as simple as just a unit conversion, right? Because concentrations can change. But the conversion between a pound mass and a kilogram is always the same. So concentration, what we're doing is we're converting between the amount of one species to the total amount. So mass and mole fractions, they count as units of concentration or composition. Right? So if we know that we have a 1 molar hydrochloric acid solution, what I'm effectively communicating is that for every 1 mole of acid, we have 1 liter of solution. Right? That's what a concentration unit is. I'm converting between how much of one species we have to the total species. So going back to the example that I just erased of our chemical plant, right? If I need to make up a solution of, let's say, 20% sulfuric acid by mixing 100% sulfuric acid with 100% water, right? Concentration is how I'm going to use to work backwards to determine, okay, how much of each individual species do I have? And that's exactly kind of what our starting sort of material balance is going to look like. So we have a number of different ways to express concentration. Molarity is one that is exceptionally common in chemistry classes and one that is very infrequently used in engineering. This is moles per liter. The reasoning behind this is that volume is kind of hard to measure. Right? Typically, if we can avoid volume, we would like to avoid volume. Mass is always easier to work in. So in engineering, we are almost always going to be talking about mass fractions and mole fractions, and infrequently are we going to be talking about molarity. Because molarity is, like I said, you need to have a constant volumetric container to prepare a solution. Right? Because if I add acid to a water, the volume doesn't stay constant. Right? It expands a little bit or contracts a little bit, so keeping volume constant is actually kind of a real pain. We also talked about mole fraction, mass fraction. Right? Those are defined over there on that board. Right? So these are units of concentration. Again, we're converting between the amount of one species in the system, or it could be a combination of species too, right? For example, we could have a lot of different hydrocarbons dissolved into water, right, as a contaminant. We could say, what's the total concentration of hydrocarbon contaminants? In which case, it wouldn't just be one species, it would be a combination of species. But again, we're converting that to the total amount of material. A couple of other units that we're going to encounter are parts per million. ppm is equal to parts per million. Or ppb, parts per billion. And if you actually, I don't know how many of you are homeowners, but like you get a report of your water if you're a homeowner, and it basically says, oh, we tested your water and it's got parts per trillion of arsenic in it, and things like that. So you even have parts per trillion. But anyway, so a ppm of species I is effectively just equal to its mole fraction times by 10 to the 6, which is a million. Parts per billion is equal to the mole fraction times by 10 to the 9th. The reasoning behind this, nothing more than convenience. So when I look at a sheet of paper, I don't want to see 0.000000007. I'd rather just see 7 ppm. I don't know if I counted the zeros right. So for gases and vapors, these typically correspond to mole fractions, right? So parts per billion really actually is counting the number of particles and saying 1 in a million or something like that. For liquids, this is typically mass fractions. Just a convention, something to remember, but even on an exam setting, if I ever give you units of ppm, shoot your hand up and say, are you talking about mass fraction or mole fraction? I'm not going to hold it against anyone to remember those exact nuanced details there. Okay. Any questions so far on units? So we've got a skosh amount of time left, so we're going to introduce pressure. So the last two units that we have to talk about are pressure and temperature, and they are going to be of our more complicated units that we'll be talking about. So far, I think most everything we've seen on the board should have come up at some point in a chemistry class, most likely. Whether it's organic chemistry, general chemistry, lab classes, or whatever. So pressure and temperature are a bit more complicated because it depends on the reference state, right? There are different types of pressure. There's absolute pressure, there's atmospheric pressure, there's gauge pressure. So what those tell us is what is the reference state, just like with temperature. There's absolute temperature and there's relative temperatures, right? Does anyone know what's an absolute temperature scale? Kelvin. What's a relative temperature scale? Okay, now what's the same thing for American engineering units? Rankine and Fahrenheit. So pressure and temperature, they both depend on what reference you're referring to, so they are a skosh bit more complicated. So pressure is equal to a force over an area. What are the SI units of pressure? Anyone know? It is a Pascal. So a Pascal is defined as a Newton per meter squared. What's a Newton? I think I heard it as kilogram per meter second squared, right, which is a mass times an acceleration divided by meters squared. And so we can find that the base units for a Pascal are kilograms per meter second squared. Well, that means a whole lot. But that's what it is. Actually, what it turns out to be. So, 1 Pascal is actually a very, very, very small amount of pressure, right? Imagine a 1 kilogram mass, which is like, I don't know, a really small ball of lead, distributed over an entire square meter of area. Look, that doesn't, if someone put that on me, I wouldn't feel like I was being squeezed out. So as it turns out, 1 atmosphere pressure is equal to approximately 1.01 times 10 to the 5 pascals. So 100,000 pascals is the force that's pushing on every one of us right now, from the weight of the air from outer space all the way down to this level. And in fact, since we're higher up, it's not quite the same. So in general, it's better to write this as 101 kilopascals. But the SI unit is the Pascal. So typically, if you look in the back of your book or different things, you will not ever see pascals presented. It's usually atmospheres or bars. Because nobody wants to write 101.5 or 101 times 10 to the 5 every time they write down the units of pressure. So if we visualize pressure, right, let's say, for example, I'll draw this vertically. We have a glass of water. Flow of a fluid is driven by a pressure differential. So if I have a glass of water sitting here and the water's not jumping out and the air's not rushing in, that means the pressure is equal at that interface. So how pressure is defined then is if I have a gas particle, it's physically hitting that interface and pushing down on the fluid. Likewise, in the liquid, there are lots of different particles hitting off. So in order for the pressures to be equal, that tells us that our gases are flying in and hitting the interface with a higher overall force, but you have more overall collisions of the liquid on the same interface, right? So the net force of those molecules pushing on the interface from both sides is going to be equal, and then you won't have flow. But if you take, like I say, for example, like a bucket of water and you drill a hole in the side of it, the reason why that flows out is because the pressure at the bottom of the bucket is higher than at the top, and so it's, the water on top is physically pushing it out. The area around the bucket is at atmospheric pressure. So you have a higher pressure at the bottom of that water column than you do in the surrounding areas. Now we call that hydrostatic head. Where's my eraser? So a column of fluid, just like how air in the atmosphere pushes on us right now, gives it pressure. So if I have a column of fluid with height h, the pressure at the bottom of that column of fluid is given by the equation P is equal to rho g h plus P naught, in which case this is the pressure pushing on the top of that fluid column. So in the case of our atmosphere, there is no pressure pushing on the top because it's outer space, and there's nothing on outer space really squeezing Earth in. It's just the gravitational force. So we have the density of the fluid. The higher the density of the fluid, the more force is exerted. G is the gravitational acceleration, and then H is the total amount of fluid, or the height of the fluid pushing down. And this is called hydrostatic head. Head or pressure.
And so that's the same as pressure, right?
Yes.
Hydrostatic head is.
Yeah, head and pressure are synonymous terms. So sometimes in your senior design class, you'll find that a particular pump will give you 30 feet of head. But that basically means that it can pump water 30 feet into the air, and that's the maximum amount of pressure that it can deliver. So if we were to go swimming, right, moving down the swimming pool right, or going deeper into the water, you feel the pressure almost immediately. But if I climb a flight of stairs and go up 10 feet or 20 feet, I don't feel the difference in pressure. Right? That's because the density of air is so low that we don't feel much of a change. But the density of water is so much higher, about 1,000 times higher, that we see a big difference just going down 10 feet in water, and you can feel the pressure. Okay, so we're going to finish up pressure on Friday. We'll also have our first quiz on Friday, so just be prepared for that. And then we'll also finish up with temperature and move on. All right, thank you.